Welcome back, guys. Today we're going to be looking at exponent laws and inverse functions. So up to this point in this unit, we have graphed exponent functions or exponential functions. We've graphed logarithmic functions, and I've told you that they're inverses of each other. But today we're going to actually look at what an inverse function is. So the first part of this lesson is mostly a review of concepts from Math 10C. So we're going to look at exponent laws, and then we're going to get into what an inverse actually is. All right, so starting off with exponent laws, we need to go through some of those laws from before. Now, in grade 10, you would have had these on a formula sheet. Now, the expectation is that you're able to know them without a formula sheet. And so let's go through them. All right, so the first one is the product law. So when I am multiplying powers with the same base, then I'm going to add my exponents. So a power is what sometimes people will often refer to as the exponent, but the base and the exponent combined together is the power. And so the base is the bottom number, and that's going to come into play quite a bit when we get into log functions. So the base of the power is the x, and the exponent is the n. Now, when you're writing things, you want to make sure that you keep them in the correct position. So keep your n in exponent land. And when we get into logs, I'll talk about keeping things in log land. But keep your n in exponent land. So keep it up high where it needs to be. You don't want to get in the habit of writing something like this because that looks like x times n. So we don't want to see that. All right, so the first rule there was the product law. X to the m times x to the n is x to the m plus n. So when we're multiplying powers with the same base, we add our exponents. The quotient law, x to the m divided by x to the n is x to the m minus n. So when we are dividing powers with the same base, we subtract our exponents. If we're raising a power to a power, so x to the m to the n, we can multiply our exponents. So if we have a power raised to a power raised to another exponent, then we multiply our exponents. Power of a product. So the m gets distributed through, and where this one usually causes trouble is when we're dealing with a coefficient, and so we'll look at some examples there. So x y to the m becomes x to the m times y to the m. Power of a quotient, the m gets distributed throughout, so x over y to the m becomes x to the m over y to the m, and we know about restrictions now, NPVs, y cannot be 0. Integral exponent rule. So this is where we're talking about our negative exponents. Typically, we do not write our final answer with negative exponents, so x to the negative m can be rewritten as 1 over x to the m. If I had something like this, x to the y to the negative m, I could just reverse my fraction, so invert it or take the reciprocal and have y over x, and then the m would become positive. Okay, so those are ones you would have been introduced to in grade 10. And then rational exponents. So x to the m over n becomes root n times x to the m, or the nth root of x all put to the exponent m, which can also be written as x to the 1 over n to the m. So the way that I used to remember this is we got the guy living in the basement, and we're going to kick him out the door. So we've got this n gets kicked out the door, and then the m stays inside. And then again, that can also be the nth root of x to the m. Now the next one here, we've got x to the 0 equals 1. So this is just a rule that we remember. Anything to the exponent of 0 is 1. Now, why might that be? Well, if we look at our exponent rules, x to the 0 can be written as x to the n minus n, because n minus n is 0. If we were to write that as a product, it would be x to the n times x to the negative n, because x to the n plus negative n is the same as x to the n minus n. We can also write it as a quotient, x to the n over x to the n, and anything divided by itself is 1. So it's not so much important that you can show me why x to the 0 is equals 1. It's that you remember that x to the 0 equals 1. But just in case you were curious as to why that is, I've got that shown there. All right, so let's get right into some examples here. So our first one here, we've got a to a squared times a to the 4th. A squared times a to the 4th. We are multiplying powers with the same base, so we can add our exponents. So a to the 2 plus 4 becomes a to the 6. 8x to the 5 divided by x cubed becomes x to the 5 minus 3, which is x squared. If we have t to the 7 raised to the third power, so t to the 7 cubed, this becomes t to the 7 times 3, which is t to the 21. If we have x squared over y, our cubed is going to come in, and there's a little 1 there that you can't see but we know is there. This would give us x to the 6th over y cubed. Now, some people might want to divide these out and say, well, 6 minus 3 is 2. We can't do that because they're not the same base. All right, E is the one that usually gets a little bit tricky. Sometimes people want to bring this in and they just want to say 5x cubed, but we have to bring that 3 into both. So if I were to rewrite this, this is like saying 5 to the 1 times x cubed and then cubed. So I still follow the same exponent rules. 3 times 1 is 3, x times 3, oh, sorry, that's a 1. 1 times 3 is 3. So we have 5 cubed times x cubed, and 5 cubed is 125, so 125x cubed. The other one that can cause some trickery sometimes is that negative in front of the 2. So we could bring these in. This is negative 2 to the 1, or you could think about it as negative 1 to the 1 and 2 to the 1 and so on. But this is negative 2 to the 1 and b to the 1, all put to the exponent of 4. So when we bring that 4 in, this becomes negative 2 in brackets to the 4 and b to the 4th. So if you were to go on your calculator and put negative 2 to the 4th or negative 2 in brackets to the 4th, you'll get different answers because negative values put to an even exponent should be positive. So negative 2 to the positive 4, or negative 2 to the 4 exponent 4 is 16, b to the positive 4. Now, if you were to put this in your calculator and miss the brackets, you'd end up with a negative 16 and we'd end up with a wrong answer. So those negatives can be a little bit tricky sometimes. All right, let's take a look at the next examples here. Example 2 says to simplify each expression and write using positive exponents. So if we get a negative exponent, we're going to use that rule right here, the integral exponent rule, that says x to the negative m is 1 over x to the m. So we're just going to flip them to the reciprocal position. So x to the negative 4 becomes 1 over x to the 4, because this is like x to the negative 4 over 1, so we just take the reciprocal. If we're multiplying powers, we multiply our numbers with our numbers, so 2 times 4, and then we multiply our exponents with our powers with our powers. So n cubed times n to the negative 5, 3 plus negative 5 is negative 2. So 8n to the negative 2. Bringing in our exponent here, we've got 2 to the 4th and p to the 12th. So 2 to the 4th, p to the 12th. 2 to the 4th is 16, p to the 12th. All right, now when we bring in this cubed, we have to remember there's brackets there. So the first bracket is like the come on in sign, and the second bracket is like the stop sign. So we have 5 times 3 cubed x to the 6th. 3 cubed is 27. So 5 times 3 cubed, or 5 times 27 to the 27x to the 6th. 5 times 27 is 135. So 135x to the 6th. Now, if you ever wanted to check your work with exponent laws, it's just a matter of making up some random value for x. So if I wanted to check to see if this worked, I could go 5 times 3 times 1 squared, all cubed. And I could plug this into my calculator, 5 times 3 times 1 squared, and then cubed. And I could also type in 135 times 1 to the 6th, and I should get the same answer. So if you wanted to check those, you certainly could. All right, another way to do that would be to graph both on your calculator and trace at your x values. All right, so for the next one here, we've got 6x to the negative 3 over x to the 1. So we're going to have 6 and x to the negative 3 minus 1, which becomes 6x to the negative 4. But we want to write our exponents as positive exponents, so it's going to be 6 over x to the 4th. And the last one here, we've got 12 divided by 3 is 4. And we've got m to the negative half, negative 1/2 minus 1, which equals 4m to the negative 3 over 2, which can be then written as 1 over 4m. Oh, sorry, no, the 4 doesn't move. So the 4 stays locked in place because it has a positive exponent. So we're going to have 4 over m to the 3 over 2. So what I was just doing there is sometimes a mistake that people will make because we're moving the m to the base or to the denominator. Sometimes people will want to move the 4 to the denominator as well, but the 4 has a positive exponent because it's 4 to 1. So 4 to the 1 stays on top, and then m to the 3 over 2 moves to the bottom. All right, now this could also be written as a radical. We could write that as 4 over the square root of m cubed. Would be another way to write it, but I'm just going to leave it like this. All right, so next example here, it says, without using a calculator, determine the exact value of the following and then verify with a calculator. Well, if we want to do these without using a calculator, that means we need to use our exponent rules. So 3 to the negative 2 is 1 over 3 squared, and 1 over 3 squared is 1 over 9, and that would be our exact value. Now to check this on your calculator, you would just go 3 exponent negative 2. All right, for letter B here, we've got 16 to the 3 over 2. Well, this is our rational exponents law. So if I have x to the m over n, the n is going to get kicked out the door, and m is going to stay home. So we're going to have the 2 get kicked out the door. Now, if it's a squared, we don't actually have to write the 2, the index 2 there, but you can. And then we've got 16 cubed. Now, I don't know what 16 cubed is off the top of my head, but this can also be rewritten as the square root of 16 all cubed. Well, the square root of 16 is 4, and 4 cubed is 64. Next one, 18 to the 0. Well, anything to the exponent of 0 is 1. So 18 to the 0 is 1. Now be careful, if it was this, negative 18 to the 0, this would actually be negative 1 because 18 to the 0 is 1, and negative 1, this means negative 1 times 18 to the 0. This would be negative 1. If, however, it was negative 18 in brackets to the 0, then it would be positive 1. So just be careful of the negatives. They can cause some frustration sometimes. All right, we've got 81 to the negative 1/2. This is the same as 1 over 81 to the 1/2. Writing that as a radical, that's 1 over the square root of 81 to the 1, or 1 over square root of 81, which becomes 1 over 9. All right, so hopefully that gives you a quick refresher on exponent laws. We're going to be using exponent laws, especially when we get into solving equations. So if that's something you need a refresher on, do some of the practice questions in the examples. But we're going to move on here to inverse functions. All right, so we're going to just go through a couple investigations here and look at what an inverse actually is. So first of all, going back to some of the words you would have used in grade 10, or you would have been introduced to in grade 10, a function or a relation maps each element of set A, and set A would be our domain, to the elements of set B, which would be our range. So this is something called mapping notation. We've used this before, especially in grade 10. We have our domain 1, 2, 3, 4, and these would map to B. And so the relation says that A is half of B. So 1 is half of 2, 2 is half of 4, 3 is half of 6. And so it's showing us our domain being 1, 2, 3, 4, and our range being 2, 4, 6, 8. And then if we were to write those as coordinates, we would have 1, 2, 2, 4, 3, 6, and 4, 8. Now the inverse of a function undoes what the function or the relation does. So in other words, we reverse them or we flip them. So the inverse of a function, instead of half of, the opposite of half of would be double of. So we rewrite these and notice that our A's and our B's have flipped. So now we say B2 is double of 1. 4 is double of 2, 6 is double of 3. And again, our domain would be 2, 4, 6, 8, range would be 1, 2, 3, 4, and we can write our coordinates. So if you're looking here, if you're noticing already, our A values become our our x values essentially become our y values of the other function, and our y values of the first relation become the y values of the second relation. So the question here says to graph the original function and the inverse of the function using two different colors. So I graphed them ahead of time here. So the first one here, first function, I click on it. Actually, graph the first and the second there. So the first function here is in green. Okay, and the second function here is in orange. So these are our two functions, and if you notice, they kind of look like they're mirror images of each other. And so if I were to click right here, this is my mirror image line. So inverse functions actually have an axis of symmetry. So they have a mirror line that goes between them, and that mirror line is y equals x. So all inverse functions, an original function and inverse function would be reflected over the line y equals x. All right, so let's take a look at our function here. So the function, or maybe a better word to use here, is relation. In this case, these are functions, but sometimes they're not always functions. But if we're looking here, the function is half of, we had our coordinates 1, 2, 2, 4, 3, 6, 4, 8, and our inverse was 2, 1, 4, 2, 6, 3, and 8, 4. The equations for those would be y equals 2 times x and y equals 1/2 times x, and our domain came from what we had written before. Notice that the domain of the first function becomes the range of the second function. The range of the first function becomes the domain of the second. So, as we already talked about, notice that the x and the y coordinates in the functions have been interchanged to get x and y of the inverse. So when we're going from original function to inverse, we literally just flip all of our x's and y's. So if we were plotting these on a graph, if I gave you the function and I asked you to graph the inverse, you would literally just flip all your x's and y's and replot. So if we're trying to find an equation or the inverse of an equation, these are our steps here. We're going to interchange x and y to get the original equation, and then we would solve the equation for y and write it in the form y equals x. So I can show you how we do that here. So we have y equals 2x. If I want to find the inverse of that function, the first step is to flip x and y. So x equals 2y, and then I have to solve for y. So solving for y here, I'm going to divide by 2. And we would have x over 2 equals y, or we could write it as y equals 1/2 x. And so notice there's our inverse in our equation. All right, continuing on here. We've got another example here, and it says the first diagram shows the relation is the square root of. So -2 is the square root of 4. 2 is the square root of 4. -3 is the square root of 9, and so on. And we're asked to complete the second diagram to show the inverse of the relation. Well, when we're doing the inverse, that means that we're flipping our x's and y's. So now 4 and 9 become our x's, and our y values become -2 and +2. We have -3 and +3. Now, if we were to write what our relation is here, 4 is the square of -2 and +2. So is the square of. So 4 is the square of -2 and +2, because -2 squared is 4 and 2 squared is 4. So our inverse, the rule is the square of. If we were to write that relation in words. Now looking at our coordinates here, for the first one here, our coordinates were -2, 4, 2, 4, -3, 9, and 3, 9. And then we write those in set brackets. For the second one, our coordinates were 4, -2, 4, 2, 9, -3, and 9, 3. Now, going back to grade 10, in grade 10 we talked about the difference between a relation and a function. A function is just a special type of relation that has a one-to-one correspondence. The first example here is a function because I have only one input for every output, but our second one is not a function because we have repeating inputs. Now that's not anything you have to be able to explain right now, but I just wanted to point that out. That's something that you've learned in the past here. So if I want to write the equation that shows that x is the square root of y, then I would write y equals x squared. Because to get x by itself, we would have to square root the y. So x is the square root of y. If we wanted to write the inverse function, we literally just flip our x's and y's. So x equals y squared. Now, graphing this on your calculator can only graph positive, or can only graph functions. So if I wanted to graph this on my calculator, to get y by itself, I'd have to square root. I'll just write this up here. If I had x equals y squared, to get y by itself, I would have to square root. But I have to remember that when I square root, that's plus or minus. So in my calculator, if I wanted to graph this, I'd have to graph y equals root x, and I'd have to graph y equals negative root x. So I'd actually have to graph it in two parts on my calculator. Now the domain, just if we was looking at the domain of just these coordinate points, my domain would be -2, 2, -3, and 3. If I'm going to graph the function though, I'm just going to graph the function first and then I'll do my domain and range. But if I was looking at the domain just for the points that are here, I would have -2, 2, -3, and 3. My range would be 4 and 9. For the other one, my domain would be 4 and 9, and my range would be -2, 2, -3, and 3. But I want to look at what the domain and range would be if I actually graph the full function. So the question here asks you to graph the original relation, graph the inverse, and then draw the mirror line. Again, I've done this already on the computer. So if we click on this here, my original function is the one that's opening up here. So I have my original function is the parabola opening up. And then my inverse function is the one on its side. And again, if you wanted to graph this on your calculator, you would have to graph this in two parts. And then my mirror line right here, the dotted line, is y equals x. So the mirror line is y equals x. If I look at the domain of my original function, the domain of my original function is x is the element of reals. And if I look at the range of my original function, it's y is greater than or equal to 0. If I look at the domain of my inverse, x is greater than or equal to 0, and my range is y is the element of reals. So notice that the values of my domain and range are literally just swapping spots. So x is the element of reals becomes y is the element of reals. Y is greater than or equal to 0 becomes x is greater than or equal to 0. All right, now let's take a look at what we've learned so far. So if we're trying to find the inverse of a relation or a function, if a function or a relation is defined by a set of ordered pairs, then the inverse is defined by just switching our x's and y's. So we just interchange x and y's. All right. If a function or a relation is defined by an equation, the inverse comes from doing two steps. First, we swap x and y, and then we solve for y. And if a function or relation is defined graphically, so if you see a graph of a function, again, we can just flip all of our x's and y's, find some points and flip them, but that graph is reflected in the line y equals x. And then finally, the domain of the inverse is the range of the original. So the domain of the inverse is the range of the original function, and the range of the inverse is the domain of the original. So our domain and ranges swap. All right, let's look at two examples here where we look at finding the inverse of an equation. So going back to the example we did earlier, the first step is to swap x and y. So we're going to rewrite this as x equals 5y minus 6, and then we just solve for y. So the first thing we're going to do is add 6 to both sides, and that gives us x plus 6 equals 5y. And to get y by itself, we're going to divide by 5. Rewriting that gives us y equals 1/5 x plus 6 over 5. Now, some of you might have also done it this way. You've got 5y equals x plus 6, and when you divide it by 5, you just divided the entire thing by 5, or so the entire expression by 5. That would have given you y equals x plus 6 over 5. That will still break down to x over 5, so 1/5 x. It will still break down to 1/5 x, or x over 5, and 6 over 5. So we still get the same answer. Y equals 1/5 x plus 6 over 5. All right, taking a look at the next example here, I've got x equals 1/2 y minus 3 over 4. And after I've interchanged them, the next step is to solve for y. So in order to start manipulating this equation, I don't really want to have to work with a lot of decimals. So the first thing I'm going to do is I'm going to get rid of my denominators. So I'm going to multiply everything by 4. And in doing so, I can eliminate my fractions, and then I don't have to worry about the decimals. So multiplying that through, I'm going to have 4x equals 4 times 1/2 is 2, so 2y. 3/4 times 4 is minus 3. To get y by itself now, I'm adding 3 to both sides. Now, if you hadn't got rid of the fractions, because these happen to be nice decimals, you would still be able to get to your answer. But if these fractions were like repeating decimals, like 1/3 or 2/3, you definitely want to get rid of those fractions. So adding 3 to both sides, I now have 4x plus 3 equals 2y. Getting y by itself, we divide by 2. And that gives me 4 over 2, which is 2x, plus 3 over 2 equals y. So rewriting that, that gives me y equals 2x plus 3 over 2. All right, so that's just a refresher on exponent laws and an introduction to inverses. Take some time to do a couple practice questions, and we'll see you soon.